Okay, so this is our March test review we were going to have on the 25th, which is tomorrow. But we won't. I'll open it up and maybe you guys can give it a try. It won't count against you. It could count, I could count it for you. Maybe I could count it as a retest from the last test if you want. The questions on the multiple choice part will be just like this, and they'll be just like the ones you had on the last test. So just as a review, this is just to keep you, so you don't forget anything. This is all just going over the same stuff over and over again, so we can remember it. And, hopefully start to understand it better each time. So the first question is about which one of these choices is not required to ensure that stock solutions are free of contamination. So all of these things would keep your solution free of contamination, right? If you the stock solution bottle is the one that you all that everybody uses, so you want it to be not contaminated. So you wouldn't put your pipette in the stock solution bottle. You would replace the tops on those bottles so things can't get into it from the air, and never return. You wouldn't pour your extra stuff back into it. All right, all those would keep it free of contamination. So the one that doesn't really matter for contamination would be storing them all in a brown bottle. That would keep the light out, but that doesn't have anything to do with contamination. Contamination is actually something getting into the solution that doesn't belong there. The physical process of evaporation involves overcoming intermolecular forces. Evaporation is going from a liquid to a gas. So to change to that phase, the difference between a liquid and a gas is that there's, the forces between the molecules are gone. They're not being held together. So for this one about finding the volume, if you have a weird shaped object like a rock, we do it by displacement, and this is called displacement because what you do is you put the rock into the cylinder and it pushes the water up. It displaces the water. So here you have just water. You have 65 milliliters of water. And here with the water and the rock, you have 90. So the difference between those would be the volume of the rock. So what you would do is you would take 90 minus 65. And that gives you 25. All right, and and that is called displacement. Finding the volume by displacement. Here you have hydrochloric acid, and you need 9.7 milliliters of it. So, that many milliliters, that would be a graduated cylinder. It's very precise. You want 9.7, so you want something more precise. For the mole ratio, you have 6C4H10, right? So that's this right here. And you have CO2 right here. The mole ratio would be the ratio of the coefficients. So there's 2 moles of the CH or C4H10, and there is 8 moles of the CO2. All right, and so that reduces to, they're both even, so you can divide both of them by 2. So that comes down to 1 to 4. All right, 1/4, 1/4. 2 divided by 2 is 1. 8 divided by 2 is 4. All right. Remember, ratios are always reduced. All right. And the moles are the coefficients in front, the 2 and the 8. All right. So it says which of these things would not be a concern. So if you're looking at here where it says precautions, the only one that is 0 would be flammability. And here now we're looking at the coefficients to balance it. So those would be the numbers in front to balance the equation. So what I'm going to do is I'm going to list out my elements. I have aluminum, I have hydrogen, and I have chlorine on the left, and then I have those same things on the right. And I want to have the same number on both sides. So over here I've got 3 chlorines. These are my products, right? I have 3 chlorines over here, so I need to have 3 over here. So if I put a 3 right here, that would give me 3 chlorines, right? So I would have 3 and 3. Oh, but I need to have over here, but that would give me 3 hydrogens here, right? And I have 2 hydrogens. Looking at this subscript here, I have 2 hydrogens. So that is not balanced. All right. So it's kind of like when we were writing, figuring out the formula. I want to have the least common multiple between 3 and 2. So if I count by 3s, that would be 3, 6, 9. And if I count by 2s, that'd be 2, 4, 6, 8. So they both have 6 as a multiple. So how can I get 6 on both sides? Well, I would 2 times 3, right, would give me 6. So I'll put a 3 in front here. 3 times 2, that gives me 6 hydrogens over here in my products. And now I want 6 over here. So I'm going to erase this 3, and I'm going to make that be a 6. So I have 6 hydrogens. All right. So now I have 6 hydrogens, 6 hydrogens here. But now over here I have 6 chlorines, right? So I need to have 6 chlorines over here. So I'm going to erase this. I have 6 here. Over here I had 3. So 3 times 2, right, would give me 6. So I'm going to put a 2 in front. 2 times 3, that gives me 6 chlorines. And then I have 6 chlorines over here. So my chlorines are balanced, my hydrogens are balanced, and then now let me look at my aluminums. I have 2 aluminums here, so I need 2 aluminums here. And that's great. I saved that for last because I can put any number I want. That doesn't change anything, right? That's easy to balance. So I've got 2 aluminums for the reactants and 2 aluminums in the products. And I'll just do a last minute check. 6 hydrogen, 6 hydrogen, and then 6 chlorine, and 2 times 3 is 6 chlorine. So they're all balanced. So these are the coefficients, are the black numbers, the big numbers in front. And those are the numbers you can change. You can't change the subscripts. So I've got 2, 6, 2, 3. So 2, 6, 2, 3. So G is my answer, right? Oh, it doesn't. All right, so G is my answer. I'll go ahead and box it. 2, 6, 2, 3. Those are the coefficients that are going to balance the equation. All right. And that's the new stuff that you guys are learning online. Distance, from the distance. No worries. Okay, here we go. So how many elements are in ammonium hydroxide? So I have nitrogen, right? You have a hydrogen, and you have oxygen. Those are elements, all right? So you have three different elements. In this picture here, it says we've got the Lewis structure, all right, of a molecule. So, and the molecule is named X, right? And it's diatomic, right? You have two X and X, all right? So that would be like X sub 2, right? You have two of them. And I guess all of these are diatomic. So, well, oxygen, fluorine, and nitrogen. So I'm going to count up how many electrons are in the outer shell. So there's 1, 2, 3, 4, 5. So looking at the periodic table, which one of these has 5 valence electrons? 1, 2, 3, 4, 5. Nitrogen has 5 valence electrons. Oxygen has 6. Sulfur has 6. And I think, what was it? Fluorine has 7. So the only one that has 5 would be nitrogen. And remember, so because these are double bonds, so they're sharing. These 3 go with this element, and these 3 over here are with this element. Okay, so that would be N2, nitrogen. All right, which of these laboratory techniques are best to separate solid from a liquid? Well, that's how you would filter it. That's what we do, and you're recovering the liquid. It's like when you're making coffee. You pour the liquid into the filter, and then what you're going to keep is the liquid. You use a filter for that. All these other things would get rid of the liquid. All right. So we've got heats of vaporization. So that's where it goes from liquid to a gas, right? So at the molecular level, if something's going from a liquid to a gas, and it takes more energy, right? The water, it takes more energy. It takes 40.7 kilojoules. This is energy compared to the ammonia. So it takes more energy. That means it has a stronger intermolecular attraction if it takes more energy to break those bonds, those attractions. Name the salt formed by the neutralization of hydrochloric acid and sodium hydroxide. So neutralization is where you end up with salt and water, right? So that means this hydrogen would mix with this hydroxide, and you would get H2O. So that's going to be your water. So what's left is sodium chloride. And remember, if you're measuring, and this goes out to centimeters, and then you've got in here, you know exactly what the you know exactly how many millimeters you've got, right? These little ones are the millimeters. That means I can go out to the hundredths place, all right? If my precision here is centimeters. And I know the millimeters for sure. The guess is the in between the millimeters. Which of the following best describes why an experiment should be repeated? Well, you want to verify your results, all right? You're not trying to organize anything. You're not trying to make it more complicated. And because you can only have one variable, and then you definitely don't want a variety of results, all right? You want to get the same thing every time. So here we have this reaction. I have 2 reactants and I have 1 product. So that's got to be synthesis. All right. Synthesizing. I'm putting things together and I'm making one thing. Water can be made to boil above the natural, the boiling point of 100 degrees. So if it takes more energy to heat it up, that's because there's less air pressure. Air pressure heats things up. High pressure makes things hotter because they're all close together. So if you decrease the air pressure, then it's going to take you more energy to heat things, to get things boiling. A student, and we'll talk more about that in our next unit, but I just wanted to throw that out there because we have talked about boiling points and molecules. So if you think about it, it kind of makes sense. But we will definitely go into that more later. A student hypothesizes that the solubility of a particular solute in the water is nearly constant as the temperature varies, which the student can best test the hypothesis by doing which of the experiment. All right, so we want to have a variety. Our IV is the temperature. We're changing the temperature. And that has to do with, and that's the only one that matches that would be J. And then now this, which of these elements is found in a family, which is like a group with the, so that's a column with the above electron configuration. So you've got, doesn't matter which level, but it's at the P3. So we need to look at the periodic table. So here would be our S2 and P1, P2, P3. So it's got to be in this group or family. Nitrogen, phosphorus, arsenic, antimony. Let's see what the choices were. One, two, three. Oh, SB, antimony. Okay. So, all right. When examining the physical properties of an unknown substance, which is unsafe to observe, taste, right? We never taste anything in the lab. And examine the graph of the temperature of a compound versus heat added to the compound. So here's the temperature of the compound, here's the heat added. What is happening as it's heated from X to Y? So as we're heating it, it is changing of phases. So here it would be a solid, all right, and then it freezes, or excuse me, it melts, a solid melts to be a liquid, right? And then the next thing it would do, it would evaporate and become a gas. All right, so we've got a solid to a liquid to a gas. Remember, this would be your freezing, melting, and this would be your evaporation and sublimation. What's the condensation? All right. So covalent bonds mainly occur between non-metal. So a student wanted to calculate the formula for hydrated copper sulfate after careful massing. So you're checking the mass on a scale. You heat the compound to remove the water. And she calculated the formula to be copper sulfate with 4 moles of water. And the actual formula had 5 moles of water. So there was, she calculated to have 4, but she was supposed to have 5 molecules of water. So what would cause that error? Which of these errors matches her calculating less water? Well, it would be J. the water was not completely evaporated from the compound. That's definitely something that could happen. It's hard to tell exactly when all the water is out because you don't want to catch it on fire. All right. So what is the mass of 2 moles of mercury oxide? So if I want the mass, I'm gonna always look at the periodic table of elements. All right. So mercury is, where's mercury? Here's mercury. The mass of it is 201 if we round up. All right, so we've got 201 for mercury. Plus, we have oxygen, right? So what is the mass of oxygen? I'm going to look on my periodic table. And oxygen is 16, and a lot of you probably know that by heart. 16. We add them together, so that would be about 217 grams, right? Mass is always grams. And the units tell you what to do. If you're finding grams, think periodic table. So now it says when an ionic compound is named, the name of the monatomic anion has the following suffix, so that's at the end of it. So if it's ionic, it ends in "ide." All right. If you have copper 1 bromide, copper 1 means you have copper, and it's a +1. That's what that means, right? Copper is a transition metal, so that tells you the charge is +1. And then bromide is -1. So the formula would just be CuBr, right? Because that adds up to 0. To be sure about the bromide, check your periodic table. Oops, I didn't want to do that because I want to know what group it's in. This is in group 17, so it needs 1 more. So that would be a -1. It's going to gain 1 electron. So it's -1. All right, so now we have a student using a mortar and pestle to crush these marble chips. All right, 1 gram of marble chips, and they're in the test tube. A whole marble chip is placed in a second test tube. So you have crushed marble and a whole chip. And then you're going to add hydrochloric acid to each test tube, but the same amount, right? That's a constant, same amount of acid. The bubbling speed is noted. So what you're measuring is the bubbling speed. So that's your dependent variable, all right? The experiment is designed to study the effect of the, and so what did we do? What was different? All right, this is the dependent variable, the bubbling speed. What was different was some was crushed and the other test tube had a whole one.